First of all, I'd like to thank the chairman for the kind presentation, and of course, good afternoon, everyone. I'm Luca Marchini, a PhD student from the University of Brescia, and today I will present this work on cavitation erosion resistance of a 1.2709 maraging steels, also known as 18 nickel 300, that was industrially developed to be printed by laser-powered bed fusion. My colleague already made an overview on this material, so I will be brief. And nowadays, maraging steels have been rediscovered thanks to their applicability to laser-powered bed fusion. And that's mainly due to their good weldability and dimensional stability. As a matter of fact, maraging 1.2709 powders are already employed to print mold insert for high pressure die casting and plastic injection mold. Thanks to the laser-powered bed fusion process, it's possible to print insert with the so-called conformal cooling channels that are extremely intricate cooling channels, as you can see from the picture, that increase the insert lifetime and the cast quality to the maximization of the extraction. Since these components are already used in the mold industry, it is clear that the general properties needed to characterize the stress on the mold are already known. Although less is known about the surface resistance of these materials, and for what regards cavitation erosion, this phenomenon can happen not only in the contact with the liquid metal, but even inside the channels of the cooling insert. In fact, as known, cavitation erosion happen when a liquid happen when a liquid experiences rapid changes in pressure, and when the pressure goes below the critical pressure of the liquid that is related to its vapor pressure, bubbles will form, and when the pressure rises up again, this bubble will collapse, generating both shockwaves and ultrasonic microjets. In order to analyze material actually used for industrial component, we have selected the Prindur powder fort and the Cryodur 2709 as a reference for the forged sample. Actually, the Prindur powder fort was developed to generate component that in the end should have the same hardness, around 54 Rockwell, as the forged component. And since the reason of the development was the aim of the development was this level of hardness, the chemical composition slightly differ from one ray to another, and so it is for the heat treatment. Actually, the additive sample needed just an aging treatment, thanks to the supersaturation of alloying elements enabled from the high cooling rate of the laser-powered bed fusion process. And to characterize the cavitation erosion, we followed the American standard that employ a vibratory apparatus that you see in the sketch. The main component is the sonotrode. The sonotrode will vibrate at a frequency of 20 kilohertz with the tip immersed in distilled water at a fixed distance of a trace position of 0.5 millimeter from a fixed sample. The vibration will generate cavitation of the liquid near the surface sample. Here you can see the other fixed parameters, and the measurement were pretty straightforward, since when the test start, it was stopped at fixed intervals of time, and the mass was recorded, then the sample was put back at the exact same position. And here are shown the mere result of 2 tests for each kind of sample. The data are expressed as cumulative mass loss versus time. And as you can see, several hours were needed just to start the erosion process. And this time is called incubation time. And here is the first main difference. The active sample had a 2-hour shorter incubation time. But after that, the erosion rate were pretty similar and low. We had to reach the limit of 24 hours, the standard, to even have a 13 milligrams loss of material for the additive and 11 for the fourth. So both the material were extremely resistant to the erosion. In addition, at every test interruption, images by stereo microscope were taken, and you can see in the top there are the image of the sample at 4 hours. Actually, the light gray shade that you see is not a loss of material, but it's just a micro deformation of the surface, since at 4 hours there was no actual mass loss recorded. And at the bottom, you can look at 24 hours surface erosion, and that is more widely spread. The ring shape is related to the pressure field generated by the sonotron tip. And at these images, it doesn't give us much information about the cavitation erosion process. So to look more in depth, we have performed electron microscopy analysis. And here I've shown just the more relevant one for time issue. And that are the one after 4 hours under testing. You can see that in the top images, the surface of the first sample is just slightly corrugated and with some bit of the erosion initiation. And at the surface, on the other hand, at the surface of the additive sample, you can see larger craters. And what's interesting that some of them seems aligned or to follow some preferential path. So that makes us think that the erosion process starts at weaker point on the microstructure of this sample. So looking then at the microstructure of the analyzed sample, you can see that the first sample is almost completely left martensite, and we didn't detect any relevant defect. On the other hand, looking at the additive sample, we see the laser scan track, and that's because we tested the surface perpendicular to the building direction. So the first imperfection is actually related to the laser powder bed fusion process, and are the melt room boundaries that after just an aging treatment doesn't fade away. And what could be an actual defect are these microsegregation of alloying elements that from previous studies we know to generate the austenite at room temperature, that of course is way softer than the martensite. So to summarize, the aim of this work was to evaluate the erosion resistance of these additive maraging steels, and we used Forge 1 as a reference. Both the material were extremely resistant to the cavitation, to erosion cavitation. The erosion rate were low and almost analogous. The main difference was the earlier, 2 hours earlier incubation time of the additive sample. But in the end, after 24 hours, the difference in the mass loss was just of 3 milligrams. So we can say that a component generated by laser powder bed fusion could compete with a Forge 1 for what regard cavitation erosion. And for further research, could be done for shorter time interval near the incubation time to fully establish if the residual austenite is the weak point in the microstructure acting as preferential site. And that was all. Thank you for the attention. If you have any questions.
Thank you very much. We have time for 1 or 2 questions. Can you go back to where you compare the microstructure between the laser powder bed? Yeah, this one. So is it actually very prone to the grain boundaries, this cavitation effect?
We are still not sure, because the problem is that this microsegregation happens we found them both at the melt pool boundaries and inside the melt pool. So we cannot say for sure that the cavitation erosion nucleate at this microsegregation point, or is just general over the melt pool boundary? We need further studies to be sure of that. For sure, the fact that austenite is way softer than the martensite make us think that probably this should be the weaker point, but still we cannot say for sure.
Okay, thank you very much.
Thank you.
There are no further questions. Let's thank the speaker again.
Thank you.